This is the second of a three-part series that will be used as an introduction to some of the basic elements of calculus. We'll be using this introduction later on when analyzing data from a series of experiments that will be carried out, but it also can be used in general for solving pretty much any problem in the physical sciences. The example that I'm going to use today is in a sense similar to the one that was used in the first part of the three-part series, and that it involves cars, because cars are so familiar on an everyday basis to people, and also because the derivative of the position of a car gives you its velocity, and the derivative of the velocity of the car gives you the acceleration, and so it's easy to understand these features of what derivatives do for you. The particular example I'm going to use today is going to be illustrated in the first of the figures. That large circle on the left side of the figure is supposed to be a traffic circle, and we're going to be considering a car that's moving at a constant speed around that traffic circle. The y direction is selected to be in the northward direction, x is in the eastward direction, and the car is going to, or at least we're going to start measuring things for the car when it crosses the southmost part, which is indicated by that black dot at the bottom of this traffic circle. So that's where we'll start timing, and s will be the distance that the car has gone along that curved path or the circular path during some short time period. Theta is the angle through which it has gone during that same period, and r is the radius of the circle. Now theta, or angles in calculus, are almost always have to be presented in terms of radians rather than in terms of degrees. And since degrees are probably more familiar to most people, I picked the circle to be specifically easy to convert between radians and degrees. And to do that, the circumference of any circle is 2 pi times the radius, and I picked that to be 360 feet. Which means that every foot the car travels corresponds to 1 degree of angle that the car has moved through. The angle theta in terms of radians is just defined as s divided by r, the distance the car has gone along that circular path divided by the radius of the circle. And I also had to pick the speed of the car. The radius of the circle is defined by the fact that it's 360 feet around it, and that means that the radius of the circle was 57.3 feet. And so I picked the speed because it takes 90 degrees or 90 feet to go a quarter of the way around the circle. I picked the speed to be 30 feet per second, so it'll take 3 seconds to go that 90 feet to get around a quarter of the way around, and it takes 12 seconds to get all the way around the circle. The next figure will show some of this information in terms of the plots. And so the upper left-hand panel shows s, the distance that the car has gone in feet, on the vertical axis, and the time on the horizontal axis. So as we saw in the previous figure, after 3 seconds the car has gone 90 feet or 90 degrees or a quarter of the way around the circle. And the speed of the car is a constant. The distance the car has gone is equal to that speed the car was going times the time. And so s equals vt is written in as a formula in the middle of that figure. Now what we want to do is to be able to write the angles also in the similar format. And the reason is because we want to take derivatives with respect to time. And so I'd like to have time explicitly written in our formulas. And so s theta is equal to s over r, the distance the car has gone divided by the radius. And we just saw that s is equal to vt, and so you put the numbers in, and you get theta in radians is equal to pi over 6 times the time. Or you could write this as theta is equal to omega times t. The reason we do that, where omega is a pi over 6 factor. And the reason we do that is because s is equal to vt has v as the speed of the car, so theta equals omega t means that omega is the angular velocity of the car, and so omega is equal to pi over 6 radians per second. That's how far the car goes per second. Now the right hand side of this figure is the conversion between two different coordinate systems. And we noticed that you could specify exactly where the car is located if you give the radius of the circle r and the angle theta that it's gone from the bottom of the circle to the point at some certain time. So if you give r and theta, you would specify exactly where the car is located at any time. Similarly, if you gave x and y, you would be able to specify exactly where the car is at any specific time. The distances from the center of the traffic circle, which is the origin of our coordinate systems. So the plot on the upper right-hand side shows in the dashed line what we called S in the previous slide. The distance of the car is actually, that's the trajectory the car is actually passed around, going around part of the circle. And the triangle is a right triangle. So the opposite side, x divided by r, the hypotenuse, is equal to the sine of theta. In other words, x equals r sine of theta. And the cosine of theta is the distance y of that length, of that size, divided by r. But since y is negative, because we had the origin as the center of the circle, y, it starts off the bottom of the circle, or at negative y, so that the length of that y part of the triangle is equal to minus y. So in other words, y equals minus r times the cosine of theta. So that gives you a way of converting between these two different coordinate systems, the r theta coordinate system or the xy coordinate system. And this will be plotted out in the next of the figures. So in the upper left, we plot x, the distance the car is in the east-west direction, as a function of time. And it starts off at 0 because it's not in the east or west direction. It's right exactly below the center of the traffic circle at the starting point. And then it's going in the counterclockwise direction or in the positive x direction, so that the x becomes positive, and it gets a maximum of 57.3 feet, which was the radius of the circle. And then it oscillates as shown. Similarly, the y is plotted, and the y starts off at minus 57.3 feet because it's the bottom of the traffic circle, or the south side. And then it goes towards more positive directions as it curves around the y velocity or position goes around the traffic circle, and it gets more positive. Now what we want to do is to be able to get the first thing we could do is get the velocity of the car by taking dx dt and dy dt. And I picked this sinusoidal thing because sines and cosines you can look up in pretty much any handbook of mathematics and get what the derivative of the sine and the derivative of the cosine are. And they're very simple expressions. So for example, the derivative of the sine of omega t with respect to t is equal to the cosine of omega t times the derivative of omega t with respect to t. But omega was a constant, and derivatives only involve derivatives, changes in the various variables. And so you can take omega outside of that derivative of omega t factor, and you get omega times derivative of t with respect to t, but derivative of t with respect to t is just 1. And so you get omega times the cosine of omega t is a derivative of the sine. So whenever you see the derivative of a sine of omega t with respect to t, you can replace that by omega times the cosine of omega t according to the mathematical handbooks. Similarly, if you take the derivative of the cosine of omega t with respect to t, you get minus omega times the sine of omega t, again according to the handbooks. So we'll use those expressions, and we plotted those in the bottom two panels. So, and the derivative of x with respect to t would be the velocity in the x direction. So the velocity in the x direction is r times omega times the cosine of omega t, and the velocity, the component of velocity in the y direction is r times omega times the sine of omega t. So we get that from taking derivatives of the position that we had. Now just to check to make sure the handbook is correct, which of course it will be, but you can evaluate v squared and get v, which is vx squared plus vy squared, and you put those expressions in the panels right above that, and you find out that that's just the quantity r omega squared, or in other words, the speed, the magnitude of v, is equal to r times omega. And if you put the numbers in, you find that comes out to be 30 feet per second, which is what we expected. I'm going to stop there as far as the slides go, but have you try to do the next derivative, and it's just as simple as the previous one. In other words, whenever you see a sine of omega t, the derivative of that is going to be omega times the cosine of omega t. And whenever you see a cosine of omega t, the derivative is going to be minus omega times the sine of omega t. So if you take the derivative of the vx and the vy, you will get the acceleration ax and the acceleration ay in the x and y directions. And you can do the same thing I did in that check in the bottom of the thing and see the magnitude of the acceleration, and you'll find out that's also a constant, the magnitude of the acceleration, so you'll find out what that is. But more interesting maybe, you can find out the direction of the acceleration of the car as it's going around a traffic circle, because you'll have the x and the y components of that acceleration. And you'll find out that the car is accelerating at all times, all the way around the circle. It's accelerating in a direction exactly towards the center of the circle. So you'll find out some information by taking these derivatives, just for knowing that the car is going at a constant speed around a traffic circle.